So now we can apply what we've learned about electromagnetic radiation to help us understand atoms. So this is a picture of a neon sign. And the orange here is actually a glass tube with neon gas inside of it. And you apply electric voltage, and the neon gas glows neon orange. That's where the name came from. It came from the element. Really bright, bright orange color. What happens is those neon atoms absorb the electrical energy and then they re-emit it as light energy. This is a mercury lamp, very similar to this neon light. So here's a mercury lamp, and we apply voltage. There's mercury gas in here, and it gives off a blue glow. A hydrogen lamp gives off a pink color. So this was observed that different things give off different colors of light in a lamp like this. If you take the light from a hydrogen lamp, just like we saw in an earlier slide with a light bulb, pass it through a slit and through a prism, instead of getting a rainbow, you get 4 lines with a bunch of black in between. So there's this sort of red line and sort of a blue-green line and a blue line and a violet line. And you get 4 distinct lines. And that was kind of a wow moment in science. What the heck? Why does it do that? So this is what you get with white light. This is a hydrogen spectrum. If you make a helium lamp and look at its light, you get different lines. And neon gives you a whole mess of lines all over the place. The overall color that you see is a combination of all these lines together. So these are called emission spectra. And for an individual element, there are only specific wavelengths. Remember that the color is related to the wavelength of the light, which is related to the energy of the light. So these different colored lines mean that there are energies of specific levels that are being released when these atoms are excited. So why? Why does it only give off certain wavelengths of light? So Niels Bohr developed a model to explain this. It's a simple model, and it's wonderful, and it only works for hydrogen. So that's kind of a bummer. But we're going to learn about it anyway because it's still a good picture. So the Bohr model, here you have the nucleus, and what we didn't address earlier, we know that the protons and neutrons are in the nucleus and that the electrons are out here somewhere, but what the heck are they doing? Well, this was a model that's trying to explain what those electrons are doing. This is saying, well, the electrons are in orbit around the nucleus like the planets are in orbit around the sun. We can grasp that, right? And so it could be in this level, n equals 1. This is an orbit with a particular energy. Or it could be in orbit number 2. This has higher energy, and as you go up in number, the energy level, the energy of that orbit is higher. Those orbits are fixed. The distance is fixed, and consequently the energy is fixed. And the word we use to describe that is quantized. So something that's quantized, there are particular levels. If we look at this ladder, so you can stand on the first rung, or you can stand on the second rung. You cannot stand in between. You can't be in between the levels. You can only be on one level or the next level. There are a lot of things in our everyday lives that are quantized. Our monetary system, the paper bills that the United States uses. There's a $1 bill and a $2 bill and a 5 and a 10 and a 20 and a 50 and a 100. But there's no $75 bill. There's no $33.27 bill, right? It's quantized. Our coins are quantized. Grades in school, you're in first grade, you're in second grade. You can't be in 1.5 grade, right? Things are quantized. Many other things, though, are continuous, meaning you could be anywhere in between. So a ladder is quantized, but a ramp would be continuous because you could just move anywhere along the ramp. But on stairs or on a ladder, you have to be on one rung or the next rung. You can't be in between. So the orbits were specified by a quantum number, just 1, 2, 3, 4, 5, and the electron cannot exist between the orbits. So you can be in orbit 1 or you can be in orbit 2. And the other thing is, as you go up in numbers, the rungs the energies get closer and closer together. The orbits get closer together. So we can use Bohr's model to explain why we get those particular lines in the hydrogen spectrum. When a hydrogen atom absorbs energy, so energy comes in, it's absorbed by an electron. The electron gets extra energy. It can move from this lowest orbit to a higher orbit. It's not going to be stable up there. It'll be up there for a bit, and then it will relax down to a lower level. It could relax all the way back to the first level, or it could relax to the second level, anything below. But it cannot be in between. When it relaxes, that energy comes back out in the form of light. Yes?
So kind of a two-part question. First, will the electron always relax back?
Yes.
Down?
The electron will always relax back.
And so because it emits light, then would that be, like Chapter 7 said, emitting light is a chemical change? Would that relate?
You can cause something to emit light without having a chemical reaction. So just zapping an element with electrical energy will cause it to release light. That's not a chemical reaction. But when you take two chemicals and mix them together, like my kids did with the glow sticks for the 4th of July, right? That's not that you are putting energy in and then energy is coming back out. It's the chemical reaction occurring causes energy to be released in the form of light. And conservation of energy is in effect here. If the atom absorbs energy, that energy doesn't just go away. It has to come back out somehow. So the electron can get excited to a higher level, but eventually it will relax down and go back to the original. We call that the ground state. It'll be in the lowest energy orbit that it can be. And that's like all of nature is always moving towards lower energy, right? Things that are high energy are unstable. So when the electron goes back to a lower energy orbit, it emits a photon of light, a quantum of light, a packet of light energy. So it absorbed energy, and then it releases that back out as photons. The reason that we see a particular line, so for hydrogen, one of the lines is a red line with a wavelength of 657 nanometers. We can calculate the amount of energy that corresponds to that. And that is equal in energy to the difference in energy between level 3 and level 2, the orbits. The blue-green light, 486 nanometers, that corresponds to the difference in energy between level 4 and level 2. And the violet light at 434 nanometers corresponds to the energy difference between level 5 and level 2. We can measure the wavelength of the light. We can calculate the energy. And so we can calculate the energy difference between these different levels for the hydrogen atom. So the Bohr model was extremely successful for hydrogen. It predicted the lines of hydrogen emission. You could do calculations and find out all kinds of cool stuff. Unfortunately, it doesn't work with even helium that has 2 electrons. So that was a bummer. So it was replaced with a more sophisticated model called the quantum mechanical model. And this is what blows people's brains up.